Hi, welcome back to the AICE Chemistry lecture series. Today we're going to cover chapter 5, section 2, and we're going to specifically look at the gas state in states of matter. In section 1, we covered the basics of all three states of matter. We're now going to take a deeper dive into each state of matter, starting with the gaseous state here. So the gas state and gases in general are all ruled by the same theory, which we call the kinetic theory of gases. The kinetic theory of gases essentially looks at how gas particles, whether molecules or atoms, behave and what we think of what is an ideal gas, a gas that fits all of these assumptions perfectly. Now, the kinetic theory of gases makes certain assumptions about how gases behave in order to explain their behavior. The closer a gas fits these assumptions, the better we can predict how it will behave. It can be used to explain things like the effects of temperature and pressure on a gas, as well as the rate of a reaction. We're going to talk about rates of reaction in a later chapter, but for now, let's focus on how the kinetic molecular theory can explain the relationships between all the different properties of a gas: temperature, pressure, volume, etc. The kinetic molecular theory, in its basic definition, is the theory that particles in gases and liquids are in constant movement and in constant motion. And because of that assumption, and because of the fact that gas particles specifically are always very rapid movement, we have a few key points that the kinetic molecular theory makes, or the kinetic theory of gases makes. The gas molecules move rapidly and randomly. This is something that we discussed in section 1. But the kinetic molecular theory, or the kinetic theory of gases as it's called in your textbook and in the Cambridge curriculum, is going to assume that gas molecules or particles are moving very rapidly and randomly. There's nothing controlling how quickly they're moving or in which direction they're moving, other than just basic, statistics and random chance and them colliding with each other. This is a fairly safe assumption because we know gas particles have a lot of space between them, and therefore they are moving independently of each other. The second part of the theory says that the distance between the gas molecules is much greater than the diameter of the molecule itself. So the volume of the molecule is negligible. So let's look at what this means, because this is a very important assumption of the theory of the kinetic theory of gases here. What we are essentially stating here when we talk about the volume of the gas, that normally we picture molecules as being these big circular atoms or these big circular particles that are constantly moving around in different directions. Now, this in a zoomed-in view is fairly accurate, but we have to consider the difference between the size of the particle and the size of the container. If we had a container, and we'll just make a square here. So if we had a container of this size, and we talk about the particles of the gases, we have to realize that if this is the volume of a container, a particle of a gas is just a dot. And these dots, these particles, are so far apart from each other. There's so much space between the particles themselves that when we look at a container like this one, the volume of the container, or the volume of what we call the gas, if we consider this to be the size of the container, so let's say this contains 10 cubic decimeters in volume, we will say that the gas volume is also 10 cubic decimeters, right? Because if the container is this size, we said in section 1 that gases take the volume of their container. They have an unfixed volume. Then the volume of the gas is also 10 cubic decimeters. But if we look at this and we compare the amount of distance between the particles versus the size of the actual individual particles, this 10 cubic decimeters, even though we say this is the volume of the gas, it's mostly empty space. less than 1% of this whole container's actual particle space, actual particle volume. Most of it is all of this empty area in between particles. And so this is what we mean when the theory says that the area or the volume of a particle, the little pink dot, is negligible when it comes to the volume of the container or the volume of the gas, because most of the gas's volume is empty space. If we were to grab all of these particles and condense them into a single point, into a single area, the volume of that little area with all the particles will be tiny compared to the volume of this container. And so the amount of volume the molecules themselves take up is negligible compared to the amount of empty space in this gas or in this container. That's what the second part of this theory is saying. It's saying that even though we have this gas with a volume which we attribute to it, because of the empty space is so much greater than the volume of the particles themselves, we can essentially ignore the volume of the particles. The volume of the molecules or particles is negligible compared to the volume of the gas. The third assumption is that there are no intermolecular forces of attraction or repulsion between the molecules themselves. Now this again goes back to some very similar point as the last one. The amount of distance between particles is so big that, realistically speaking, the molecules or the particles are not going to have any chance to create intermolecular forces. Essentially, going back to a drawing that we had, let me get rid of these yellow lines. If we have all of these little particles around, the distance between them, so the distance from one particle to the other, is so large that there are no intermolecular forces that can form over such a large distance. And these particles are moving so quickly that even if they got close enough to form intermolecular forces, they will quickly move past each other. Because remember, these particles, even though we draw them as individual dots, they're in motion. They're going in different directions. They're moving around, which we usually show with arrows. And they're moving around in different directions. So even if two particles, like for example these two, were to move so that they're close to each other, they will quickly pass each other. Or if these particles are heading in the same direction, they will get close, but they will quickly, because they're moving randomly and rapidly, move past each other so the intermolecular forces wouldn't form. So the second assumption of the kinetic molecular theory is that there are no intermolecular forces between these particles, either of repulsion or of attraction. And so they move independently of each other randomly. Number 4 says that all collisions between particles are elastic. This means that no kinetic energy is lost in the collision. And this is a bit of a more of a sticking point because this requires some knowledge of physics, right? Usually, with collisions, we can have either an elastic or a non-elastic collision. So let's look at that first. An elastic collision is one where no energy is lost, meaning that if we have a particle moving at a specific distance, which we're going to symbolize by the size of the arrow, and that then there's another particle that's still, once that particle crashes into the other one, once this particle and this particle crash into each other, then this particle would stop moving and the other particle will move with the exact same amount of force or speed. So I'm drawing the two arrows relatively the same. I'm not perfect. But an elastic collision is one where there's a full transfer of energy. Now, this is completely unrealistic. You can't have a full transfer of energy because in all collisions, some of that energy is going to be lost in the form of heat. So, in a theoretical elastic collision, there's a full transfer of energy between particles. However, in a non-elastic collision, which is what is more realistic, what actually happens, a particle that crashes into another particle, so again, I might use the arrow to show the speed, or the force or the energy that it's moving with. Once those two particles collide with each other, the other particle is going to move, but it's going to move at a smaller speed or a smaller distance. Not all of the energy from the first particle is transferred into the second, because some of it is lost in the form of heat. That collision, let me actually put it on the other one, this collision gives off energy in the form of heat. The heat from the collision causes the transfer of the kinetic energy to not be full transfer, so there is energy lost in a non-elastic collision. Now, non-elastic collisions are realistic, whereas an elastic collision is theoretical. Because most things in the universe, or at least everything we know in the universe, crashes or collides in at least some form of non-elastic manner. All right. So that's the difference between an elastic versus a non-elastic collision. A non-elastic collision will have heat being given off, meaning that energy is lost in the form of the heat. That's why realistic is what actually happens. Think of a car crash where the crash itself creates heat. Versus an elastic collision, which is more of a direct transfer of kinetic energy, meaning that there is no energy lost. There's full transfer of energy, no energy lost. Slash. So that's what the difference between an elastic and a non-elastic collision is. Well, when it comes to the kinetic theory of gases, the kinetic theory of gases assumes that every collision is elastic. And that's where one of the kind of shortfalls of it comes from, is because collisions aren't elastic. That's not possible. We can have very elastic collisions or very non-elastic collisions. It's a spectrum. We are looking in this case at two ends of a spectrum, with elastic being on one side and non-elastic being on the other, with a whole myriad of things in between. So a collision could fall somewhere more elastic, more non-elastic, or a collision could fall somewhere more elastic. It always going to depend on the type of collision that we're looking at. But again, no collision is purely elastic or purely non-elastic. There's somewhere in between, right? And there are different types of collisions that fall all over this spectrum between the two. So this second assumption, this fourth assumption, all collisions in between particles are elastic, is unrealistic, but it is an assumption that's used to make the kinetic theory of gases more understandable. This means no kinetic energy is going to be lost in those collisions. So that's at least what the theory is assuming. And finally, and this was more of a fact than an assumption, the temperature of a gas is related to the average kinetic energy of the molecules. This is very important because this is the basis for a lot of thermodynamics and a lot of chemistry. What we call temperature, which we've measured ever since we were kids, we've always talked about temperature, the temperature outside, in science classes, the temperature of a sample, whatnot. The temperature of a gas is related to the average kinetic energy of the molecules. So what does that mean? That means the hotter something is, the faster its molecules or particles are moving. The colder something is, the less quickly its particles and molecules are moving. Kinetic energy is the energy of motion. So when we say that temperature is related to the average kinetic energy of the molecule, we're essentially saying that when we measure temperature, we are measuring the kinetic energy of the particles in whatever we're measuring temperature of. Meaning that we are measuring how fast the molecules or particles of that sample are going. Now, all of these assumptions, a lot of these assumptions at least, are very unrealistic. We already talked about how the collisions being elastic is not practical, it's more theoretical. But when we look at kinetic molecular theory, those assumptions are made in order to make it easier to work with. And when a gas fits most of those assumptions or all those assumptions, we call it an ideal gas. We call gases that fit the description of the kinetic theory of gases ideal gases. A gas whose volume varies in proportion to temperature and in inverse proportion to pressure is the official definition, and we'll talk about these mathematical relationships in a little bit. But gases that fit the description of the kinetic molecular theory, that fit all those points we just talked about, are called ideal gases. So an ideal gas obviously is a very theoretical thing. Gases in reality are not ideal, but we can discuss the gas in the context of it being ideal in order to make it easier to work with. What this does is that by thinking that gases are ideal even though they're not, it allows us to make very accurate predictions of how gases will work and of certain numbers like its temperature, its volume, etc., etc. Again, no gas is ideal. Instead, we study how closely a gas comes to being ideal. So we say some gases are more ideal, or we can say a gas is more real. Real gases are gases that do not obey the ideal gas laws and the kinetic theory of gases. And this is especially true at low temperature, high pressures. So we can look at a gas and compare it to another gas, on the carbon dioxide versus nitrogen, for example. So one of the comparisons we can make when thinking of these ideas is two different gases, so CO2 versus N2, for example. Both of these are gases, and we can compare them and say which one's more ideal, which one's more real. Or we can make a comparison of the same gas under different circumstances. For example, we could compare carbon dioxide at 25 degrees Celsius versus carbon dioxide at 0 degrees Celsius. And so we can compare conditions like we're doing here. This is a comparison of conditions. And we could say in which condition is carbon dioxide more real or more ideal. Or we could compare gases and say essentially if these two gases are in the same conditions, carbon dioxide and nitrogen, which one will be more ideal, which one will be more real. An ideal gas doesn't exist because an ideal gas has zero particle volume, meaning the particles have zero volume even though they do exist. And they have no intermolecular force of attraction. We talked about this in chapter 5. It's not possible for a gas or a particle or a chemical to have absolutely no forces of attraction, no intermolecular forces. Intermolecular forces are a fact of molecular compounds and therefore will always be present. As well as it's not realistic to think that ideal gases have zero particle volume. It's not realistic to think of a gas with no volume because those particles exist. They're made out of matter, and all matter has some volume, even if that volume is minimal and tiny. So, if we look and we start thinking about unit and measurements we can make with these gases, the volume of an ideal gas, which we'll be measuring cubic decimeters like always, it can be related to two other properties. The first is its pressure. We measure pressure in pascals, and pressure of a gas or any gas is due to the collision of gas molecules on the walls of the container. So what we call pressure is a measurement of collisions. If we have a gas, like let's say carbon dioxide, and we have it in a container, so let's again draw a container. So if we have a container, and in that container we have a gas, I'm going to draw again our little dots for our particles of a gas. Those particles of the gas are in constant motion. So these particles are constantly flying in different directions. Some might be going this way, some might be going down, some are going up. But what happens is that because these are in motion, they're moving rapidly and randomly, like we assume in the ideal gas, in the kinetic molecular gases, this particle can move and it can bounce off the side of the container. And that's going to keep happening. All of these particles are going to continually move around and eventually going to run into the wall of a container and they're going to bounce off of it. Well, when we're thinking of this ricochet, so this bouncing off the sides of the container, that's what pressure is. These particles hitting the sides of the container are putting an outward pressure on the walls of this container. This is why a balloon full of gas stays inflated, because the particles of that gas are quickly hitting the sides of the container, making it stay taut, making it stay tight. And so that's why the balloon stays inflated. It's the same with any container. Any container experiences forces from those particles crashing into the sides of the container when you have a gas inside of the container. That's what we call pressure. Pressure is simply just particles of a gas bouncing off and putting force on the sides of a container. Well, if we go back, pressure is one of the properties that volume can be related to in the ideal gas laws, or what we call the kinetic theory of gases. Ideal gas laws are the mathematical laws related to this, which we'll study in a little bit. On the other hand, volume can also be compared to or related to temperature. Now, temperature is something that we already discussed. We said that temperature is the measurement of average kinetic energy of the particles, and it is usually measured in Kelvin. Now, Kelvin is a scale of absolute temperature. What does that mean? That means there are no negatives in Kelvin. It's a scale where there are no negatives, and so when we look at Kelvin, 0 Kelvin is the coldest something can be. At 0 Kelvin, there is no motion of the particles anymore. Particles are no longer moving, and therefore we have complete stop of motion. Now, Kelvin can be related to Celsius through this equation. Kelvin is equal to Celsius plus 273. They're equivalent scales in the sense that they go up by the same amount. If I have zero Celsius, 0 plus 273 is 273, meaning that 0 Celsius is equal to 273 Kelvin. But if I have 1 Celsius plus 273, 1 Celsius is equal to, 1 Celsius plus 273, that's equal to 200, and let me put some units here. This is equal to 273 K. 1 Celsius plus 273 is equal to 274 Kelvin. So you can see as we go from 0 Celsius to 1 Celsius, a difference of 1 degree Celsius, Kelvin goes up by 1 as well. So even though 0 Kelvin is not equal to 0 Celsius, or 1 Celsius is not equal to 1 Kelvin, the change in Celsius, delta degree C, the change in degrees Celsius of 1 degree Celsius is equal to the change in Kelvin of 1 Kelvin. So this is what we call them equivalent scales, because if we go up by 1 Celsius, it goes up by 1 Kelvin, even though 1 Celsius is not equal to 1 Kelvin. Now, we use Kelvin in these equations in the kinetic theory of gases and in the ideal gas laws because it is an absolute scale, meaning the lowest temperature we could ever have is 0 Kelvin. We cannot have a negative Kelvin. That does not exist. And so this keeps the mathematics easier to work with and easier to handle because there are no negative numbers to deal with here, to contest with here. Everything is a positive number. The kinetic molecular theory and its assumption of ideal gases allows us to look at how the properties of different ideal gases are going to relate to each other. Now, when we talk about relating the properties of an ideal gas, we're talking about looking at a single gas, so something like carbon dioxide or hydrogen gas or nitrogen or argon, a single gas, and looking at how the different properties of that gas, ideal gas, if we're assuming it's ideal, change based on how we change the other properties. So, for example, we can look at the pressure relationship of an ideal gas to its volume. Now, whenever we talk about look at the relationship between two different properties, in this case volume and pressure for an ideal gas, we are assuming that all other properties stay constant. So temperature and number of moles, in this case being the other ideal or the other properties, remain constant. So N, which is number of moles, is going to remain constant in this scenario. And T, which is temperature, is going to remain constant in this scenario. So what we're looking at here is, if these two are constant, how does changing the pressure of this gas affect its volume? Now, when we look at this, we can relate this to the kinetic molecular theory because gas molecules are constantly hitting the size of the container. And that is what creates pressure. Like we mentioned earlier, pressure comes from the molecules hitting the size of the container and putting force or pressure on that container. If we decrease the volume of the gas, in theory, what should happen is in an ideal gas, the molecules are going to be squished closer together. So we can see that in this diagram, right? We have a bigger volume with the same number of molecules because the number of moles is constant. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 molecules here, and that represents our number of moles. So we have the 12 molecules here, and these molecules are constantly moving around and bouncing against the size of the container. That's what creates the pressure in this container. Well, if we decrease the volume or increase the pressure, because they're related to each other, so if we push down on this piston and cut the volume in half, or another way to look at this is if we put pressure on this piston and push it down, that cuts the volume in half, which means that the molecules, the same number of molecules, because again, moles are constant, all those 12 molecules in this diagram are now closer together, have less empty space between them, and they're bouncing into the size of the container more often. Because they are creating more collisions, there's more pressure. Because the molecules are closer together, there's more collisions, therefore there's more pressure. So because of this, we can say that the relationship between pressure and volume in an ideal gas is inversely proportional. Now, this is a word or vocabulary term that you should know from math, but inversely proportional means that when one increases, the other one decreases, and vice versa. So we can look at that in this diagram here. As the volume increases, so does the inverse, or the reciprocal, of the pressure, 1 over pressure. We here are graphing 1 over pressure because if we graphed pressure, let me make that a little better. If we graphed pressure versus volume, then what we will get is the opposite. As pressure increases, volume decreases, but it's not linear. This graph will look more like this, like a crescent shape. Because as pressure increases, as the pressure goes up, which is symbolized by moving from left to right on this graph, the volume decreases. We can see this here. If we have a low pressure, if we look at the graph, the volume is pretty high. But if we have a high pressure, looking at the graph, then the volume is pretty low. So this is a graph of pressure versus volume. In order to get a linear graph, what we do is that we plot 1 over pressure, or the reciprocal of pressure, 1 over pressure, versus volume. That gives us an increasing graph. Why? As the pressure goes up, the reciprocal of the pressure decreases. And so because of this relationship that we saw, as pressure goes up, volume goes down. Well, as the reciprocal of the pressure goes down, then volume also goes down. So as we go from the reciprocal left to right, as the reciprocal of the pressure is 0, we got 0 volume. Then if the 1 over pressure increases, so does the volume. If 1 over pressure increases even more, so does the volume. Because again, we're looking here at the reciprocal of the pressure, not the pressure itself. We're looking at 1 over pressure. So as the pressure increases, the reciprocal decreases. They have an opposite relationship. And so we see that with the volume and pressure as well. We see that relationship. So you need to start being able to read these graphs. Graph reading is something that you should know from mathematics. We now just need to compare them or translate them into a scientific environment. As the pressure increases, as the reciprocal of the pressure increases, so does the volume, because pressure and volume are inversely proportional. Meaning that as pressure goes up, volume goes down. And since the reciprocal of pressure is the opposite of pressure, then as the reciprocal pressure goes up, volume goes up. And you should be able to explain why, which is what this drawing is. You should be able to explain that as we decrease the volume, the molecules, which are constant, same number of molecules, the molecules are going to bounce against the sides of the container more often. There are more collisions, which creates more pressure. So as volumes decrease, pressure is increased because there are more collisions against the sides of the container. So that's the first relationship. Pressure and volume have an inverse relationship. The next one is with temperature. Now again, when we do these, everything else stays constant. So if we're looking at the relationship between temperature and volume here, that means that the pressure has to stay constant, and so do the number of moles, which are N. So the number of moles of the gas that we're looking at and the pressure are both going to remain constant when we're comparing temperature to volume. Now, when we increase temperature of a gas, what happens is that we get more kinetic energy. Remember that temperature is related to the kinetic energy, or the average kinetic energy of the molecules or the particles of that gas. When we increase the temperature of a gas at constant pressure and constant number of moles, the molecules of the gas hit the sides of the container with more force. So because these molecules, again, number of molecules does not change. We have 6 molecules on the left, 6 on the right. At a low pressure, these molecules are moving with less kinetic energy. So when they crash into the sides of the containers, then they're hitting the side of the container with less force because the temperature is lower. So a lower temperature, lower kinetic energy, and so the collisions on the sides of the container have less force. If we increase the temperature at a higher temperature, the kinetic energy of the molecules increases. They're moving faster. We can see that by looking at how many little arrows we put on these, or little lines, and the size of the lines in this diagram. So you can see at lower temperature, they're smaller, and there's only 3 little lines. Larger temperature, bigger lines, and there's 4 of them. That is used to represent that they're moving faster. So when these molecules are moving faster in this container, when they crash into the side of the container, they're doing so with more kinetic energy. And therefore, when they crash, they put more force. Because the pressure has to remain constant, because that's one of our things here. We remain under constant pressure. The volume of the container needs to increase in order to lessen the impact of the more energetic molecule. So essentially, you can think about it this way. When the molecule crashes into this piston, because it has so much pressure, it pushes the piston up and increases the volume of the container. That increase in volume mitigates the larger force that the molecules are moving with because they have to move through a larger distance. So essentially, as we increase the temperature, because the molecules have greater kinetic energy and therefore colliding with more force, the volume of our container is going to increase. Because of that relationship, we say that temperature and volume have a directly proportional relationship. What does that mean? That when one increases, so does the other. And vice versa, when one decreases, so does the other. And we can see that in this graph that shows that volume and temperature are directly proportional. We can see here, if we have a low temperature in this graph, then if we follow the graph of volume versus temperature, we also have a low volume because the kinetic energy of the molecules is much lower. But if we have a higher temperature, then according to the graph, which is a linear increasing graph, we have a higher volume because now these molecules are moving with much higher force and therefore crashing into the size of the container with much more energy. And because the pressure needs to remain constant, pressure can't increase. So instead of the pressure increasing, the volume of the container increases. So that's the relationship between temperature and volume. So we saw pressure versus pressure versus volume, which has a inverse relationship, and temperature versus volume, which has a direct relationship. Meaning that as temperature increases, so does volume, and with pressure, as pressure increases, volume goes down, and vice versa. Let's look at how do we put all of this together when it comes to AS questions. All right. So there's only two different kinds of questions that they're going to ask you when it comes to comparing the ideal gases. The first is going to be about the limitations of the ideal gas laws and the ideal gas theory when it comes to a comparison of molecules. So what changes from this to the other type of question is what are we comparing? In this case, we're going to first look at comparing two different molecules that are both supposed to be ideal, but will differ or differentiate from ideal gas behavior or deviate from ideal gas behavior because of certain things. So the ideal gas laws have two major limitations in actuality, in practicality. The first is that there is no zero attraction between the molecules. We spent chapter 4 learning about intermolecular forces, hydrogen bonding, London dispersion forces, dipole-dipole attractions. And so saying that a gas and the molecules of a gas have zero attraction between them is not realistic. So that's a limitation of the ideal gas law. That's one point where the ideal gas law makes an assumption that we can't make fully. So that's the first assumption. The second one is that we cannot ignore the volumes of a molecule, of the molecules themselves, because molecules do have a fair bit of volume. And because we're not usually working with a room full of molecules, so we're not working with a classroom full of gas, we're normally working with containers full of gas. We can't just ignore the volume of the molecule. These limitations come into play when we're comparing how ideal molecules will be in comparison to one another. And this is the key here. We are never going to have an ideal gas. Ideal gases are completely theoretical. They're completely theoretical. We're never going to have an actual ideal gas. What we discuss with the ideal gas laws is whether molecules are more ideal or what we call more real. Real being that they deviate from the ideal gas law, meaning that they're breaking a bunch of these rules or assumptions that we're making. Normally, this type of question is asked with a comparison of molecules. So we are going to compare 2, 3, 4 different molecules and essentially say, okay, which ones are more ideal, which ones fit all of the assumptions of the ideal gas law we discussed, and which ones are more real, which ones deviate from those assumptions more because of these two limitations that we just discussed here. Essentially, when we compare two molecules, we're going to be looking at two things. One is size, and the other one is the attraction between the molecules. So when we look at a molecule, a bigger molecule with stronger intermolecular forces is always going to behave more real and less ideal than a small molecule with weak intermolecular forces. So something like ethanol, which we see here in the right side in highlighted in red, which is a large molecule with hydrogen bonding because of that OH, is going to be less ideal than something small and with weak London dispersion forces like the methane we see in green on the left side. So whenever we're comparing molecules, and that's something that you're going to be asked to do in the AICE exam, we are looking for those two things. We're looking to see which one is bigger. The bigger ones will normally have, will be more real or less ideal because we can't ignore the volume of a bigger molecule. And we're looking at which have stronger intermolecular forces. In this case, ethanol having hydrogen bonding versus the London dispersion of methane makes ethanol less ideal or more real because it has stronger attraction forces. They're not zero like the ideal gas law presumes. Now again, the ones of methane are not zero either, but they are weaker than the ones for ethanol. So we say methane is more ideal and ethanol is less ideal because methane is smaller, meaning we can ignore its volume more, and it has a weaker intermolecular force, meaning it fits that idea of zero attraction better, whereas ethanol is bigger, so we can not ignore its volume as much, and its hydrogen bonding makes it have much stronger force of attraction, deviating from the ideal gas law assumptions. So that's the first type of question we're going to be asked, where we're comparing different molecules to each other. The second type of question you might be asked is where we're not comparing molecules, we're working with the same gas, but we're comparing conditions. With condition comparisons, what we're looking at is what would a molecule be more ideal or less or more real if we increase the temperature, or lower the temperature, or increase the pressure, lower the pressure, so on and so forth. So in this case, we're not looking at two different molecules. We're not comparing methane to ethanol. We'll be comparing just one type of chemical, so just methane, at different conditions. Again, the limitations of the ideal gas that we're looking at are still the same. We're still looking at the force of attraction, and we're still looking at whether we can ignore the volume of the molecule or not. But instead of comparing these two limitations between molecules, we are looking at the condition changes that we're talking about and seeing how those condition changes are going to affect these two limitations. The limitations come into play when we're comparing conditions in the following manner. A gas that is more ideal, or a gas will be more ideal, under low pressure and high temperature. And you should be able to say why. Now, this is never going to change. It doesn't matter if the gas is methane, ethanol, carbon dioxide, oxygen. A gas is always more ideal under low pressure and high temperature. That's never going to change. What you should be able to do apart from just measuring this is being able to explain why. And again, the why falls back to these two major limitations. At higher temperatures, the molecules have more energy to overcome the force of attraction. So intermolecular forces are going to be weaker at higher temperatures because the molecules are moving much faster. Because the molecules are moving faster and have more energy, they can overcome or break those intermolecular forces more easily. This is going to lead them to have more or behave more like an ideal gas. So temperature causes the molecules to move more quickly and with more energy. So if they're moving more quickly and with more energy, there is not as much time to create intermolecular forces, and the higher energy is able to break those intermolecular forces, giving us more of that zero attraction between intermolecular forces feeling. So higher temperature means more ideal because there's more energy that the molecules are moving with, which leads to weaker forces of attraction. At low pressures, which remember, low pressure also means, because of what we just discussed, a bigger volume, because they have an inversely proportional relationship. So I'm going to put here, it's not just low pressure, it's larger volume. So at a larger volume, there is a lot more empty space between the molecules. The bigger the volume, or the lower the pressure, because it's like saying the same thing, there's a lot more empty space between the molecules in the gas. More empty space between the molecules in the gas means two things. One, it means that the volume of the actual molecules is less significant. The more empty space between molecules there is, the less significant the volume of the molecule itself becomes. Now, the second part, which is not on here on the PowerPoint, but is also important, is that because there's a much larger distance between molecules, the intermolecular forces can't form as easily. Remember, intermolecular forces need molecules to be closer together in order to be able to be created, because they're forces of attraction in magnetism. Well, the more distance between molecules, the less attraction there is between them. And the less attraction there is, the more ideal a molecule is. And so the forces of attraction are not zero when we're looking, or are closer to zero when we're looking at a much larger space between molecules, meaning when we're looking at larger volume or lower pressure. If we're looking at the opposite here, if we're looking at low temperatures and high pressure, or low volume, depending on which way we see this. So we can have a higher pressure by either having more atoms or more moles of that compound, or a lower volume. In either case, because there are more molecules per square inch, square foot, whatever, square meter, whatever you want to call it, the molecules are closer together, and we get a lot more of these forces of attraction. So I'm going to use a highlighter here to highlight these. But we get a lot more interactions between the molecules because at a lower pressure, higher pressure, lower volume, the molecules are going to be closer together. And that causes the force of attraction to not be zero. It causes them to be much stronger. And so the molecules are less ideal. Not only that, at low temperatures, the molecules are moving more slowly, which allows those intermolecular forces to be created. So at low temperature, there's not enough energy to break the intermolecular forces. And at high pressure, those molecules are closer together, allowing those intermolecular forces to be created. Additionally, if we look at the second limitation, because there is less empty space between these molecules, we now also have to consider the volume of the molecule itself. Remember, the less empty space is between molecules, the more the volume of the molecule matters, the more significant it becomes. And so with high pressure, because either the volume is lower or the number of molecules is higher, there's a lot less empty space between them. And with less empty space between the molecules means that the molecules themselves, their volume is more significant. So that brings up the second limitation of the ideal gas law. With more significant volume of the molecules, then that means the molecules become more real or less ideal. So non-ideal gas conditions, low temperature and high pressure or low volume, are non-ideal. So these molecules are going to be less ideal under these conditions. Then more ideal conditions for ideal gases is going to be a higher temperature and a lower pressure. And you should be able to explain why that's the case. With a paper 1 question though, like this one, you don't have to explain it. That's more in paper 2. But if we look at this, which substance shows the greatest deviation from the properties of an ideal gas under room temperature? So when we're looking at this question, We're being asked which substance, we're comparing different compounds. So this is like the first slide we talking about limitations. So we're comparing these four chemicals to each other: carbon dioxide, hydrogen, neon, and ammonia. Which substance shows the greatest deviation? Greatest deviation is a key word here because greatest deviation is going to mean less ideal. Remember, deviation means that it is coming away or being different from, in this case, the ideal gas. Now, they do say they're under room temperature, meaning the conditions are the same for all of them. But greatest deviation from ideal gas means which of these four are going to be more ideal or more real. When we look at this, what we have to look at is two things. Again, size and intermolecular forces. Now we can do this, and I'm going to do this here down by doing different colors. So size is a bit harder to gauge. We can normally gauge size by molar mass. And I know this is a weird idea, but essentially a molecule that is bigger in volume will also be heavier. Obviously, density, it does change from element to element, but as a general rule, we can gauge size by molar mass to make it easier on ourselves. So we can look at the molar mass of these molecules and say, okay, which one, if it's less ideal, that means we're going to need a bigger molecule. Well, looking at these, the molar mass of carbon dioxide, if oxygen has a molar mass of 16 and carbon is 12, we have 32 plus 12 is 44 grams per mole. Hydrogen has a molar mass of 1, so H2 is just 2. Neon has a molar mass of, I believe it's 10. Let's bring up the periodic table. Neon has a molar mass of 20, that is the atomic number. So neon has a molar mass of 20.2. And ammonia has a molar mass of, nitrogen is 14, hydrogen is 1, so 14 plus 3 is 17. So that's our first kind of look. We can just from this tell that hydrogen is probably not going to be the least ideal molecule. Now, just from looking at this, though, we cannot tell what the right answer is. When we look at ideal gas deviation, usually intermolecular forces are more telling than size. However, if we look at the intermolecular forces and they all have the same intermolecular force, then we will look at size instead to be able to figure it out. But we first need to look at intermolecular forces and see whether they all have the same intermolecular force. In order to do this, we will need to be able to look at the shapes and Lewis structures of each molecule. Carbon dioxide has 2 double bonds, 1 to each oxygen. Now, the bonds in carbon dioxide are polar, but because the negative poles are in opposite directions at the oxygens, and the carbon is a partial positive pole, we have no net polarity here for carbon dioxide, which means that carbon dioxide being nonpolar only has London dispersion forces or induced dipole forces. Induced dipole, temporary dipole, whatever you want to call them. Hydrogen is just 2 hydrogens bonded together with a single bond, meaning it's nonpolar, meaning it also has induced dipole forces. So it's looking like if we were to compare hydrogen and carbon dioxide, we would have to do it by size. Neon is just an atom of an element, meaning they cannot be polar, so it can only, so this has to be nonpolar. And this is true of all the noble gases, they're just an atom. So they all are nonpolar, meaning they all have induced dipole forces. It's looking like if we had just these 3 choices, A, B, and C, that we will have to look at the size of the molecules. However, if we look at ammonia, ammonia is a pyramid-shaped molecule with a lone pair of electrons on the nitrogen. Ammonia is a polar molecule which has a partial negative on the hydrogen and partial negative on the nitrogen and partial positives on the hydrogens. Not only that, but ammonia has the nitrogen-hydrogen bond, meaning that it's not only polar, that nitrogen-hydrogen bond means ammonia has hydrogen bonding. Ammonia having hydrogen bonding automatically makes it by far have the strongest intermolecular forces of any of our options. Because ammonia has the strongest intermolecular force from any of our options, that means that our correct answer is the ammonia. Yes, it is not the biggest of the molecules. Neon is slightly bigger and carbon dioxide is even slightly bigger than that, or actually twice as big as that. But the hydrogen bonding really overtakes all of the other factors. Again, we always look at intermolecular forces first when we're trying to figure out if something is more ideal or less ideal than something else. And if the intermolecular forces are all the same, like they almost were here, then we will look at size. Because size is also not only going to figure into how big the molecule is and its volume, it's also going to figure into the induced dipole forces. But because ammonia has hydrogen bonding, then that is the answer here. Hydrogen bonding, things with hydrogen bonding always want to be the least ideal because their intermolecular forces of attraction are so strong. All right, let's move on to the next slide. Now, this is all theory. We can also apply the ideal gas law into mathematics. There is something we call the ideal gas equation. The ideal gas equation is a combination of the gas laws that we know, and it looks at putting mathematics to compare the four different properties of a gas in general. Those four properties of a gas being temperature, pressure, number of moles, and volume. So the ideal gas law is the relationship between all of these things. If we are given 3 out of 4 of these properties, using the ideal gas law, we can always calculate the fourth. So again, P is pressure. Pressure will be in the unit we call pascals, PA. One of the conversions between pascals and another unit of measurement is ATM. ATM is another unit of measurement of pressure. 1 ATM is equal to 101,325 pascals. And that's something that you should probably remember in case they ever give you pressure in ATM instead of pascals, because P here has to be in pascals for us to use it. Another unit of conversion that you might be able to use or might see in the test is that 1,000 pascals are equal to 1,000 pascals are equal to 1 kilopascal. And that's, very standard. Kilo just means 1,000. So 1 kilopascal is equal to 1,000 pascals. So again, you might in a question get the pressure in kilopascals or in ATM, and you will need to use one of these two conversion factors to convert it to pascals, which is what we use in the ideal gas equation. After pascal is volume. Volume is not in cubic decimeters, and this is something you need to be aware of. Volume for the ideal gas law is in meters cubed. So you need to be aware that this volume, anytime we put it into this equation, it needs to be in meters cubed, not cubic decimeters. We have the conversion here between those two, which is that 1 cubic meter is equal to 1,000 cubic decimeters. So essentially 1 m cubed, 1 cubic meter is the same as saying 1,000 liters or 1,000 cubic decimeters. Be aware of that. This is probably where most folks get confused because we're so used to using cubic decimeters for anything relating to concentration. But in the ideal gas law equation, we use cubic meters for our volume. Next is moles. Now, N is very simple. N is just the number of moles of the gas. And it's very straightforward. It's just in moles. We do got to remember, when I talk about this in a little bit, in a couple slides, but do remember that sometimes we'll have to use the molar mass of something to figure out the number of moles. In stoichiometry in chapter 3, we learned that the number of moles can be figured out from the meters, or not the meters, what am I saying? The mass divided by the molar mass. So if they tell you something is 3 grams, instead of telling you how many moles it is of a gas, then you need to use the molar mass of that gas to convert it to moles in order to use it. And we're going to look at this in a little more detail in a couple slides. Now I'm going to skip over R for a second, and I'll go to T. So T is just temperature. Now temperature, we always use Kelvin when it comes to temperature for ideal gas laws. We're never going to use Celsius. And then remember what we talked about earlier in the video, Kelvin is equal to the Celsius plus 273. The reason we use Kelvin is because it is an absolute scale, meaning that there are no negatives in Kelvin. Everything is positive, and so it makes sure that our mathematics make sense. So we're always on using Kelvin. Now you might be given the temperature in Celsius, but you gotta make sure that you add those 273 so you get the Kelvin and use the Kelvin instead. So those are the 4 different units, or the 4 different properties of the gas. But there is a 5th letter, or a 5th thing here, and that's R. And R is a constant known as a gas constant. Now R is used in a bunch of different places, but R is a constant that makes this equation work. And the units for R are very important because they're the same units we use here in these properties. Now, in the units for R that you see on your periodic tables and on your reference sheets is joules per Kelvin mole. And you can see how the Kelvin and the mole make sense, right? We have mole here, we have Kelvin here. But how does the joules make sense? Well, 1 joule is equal to a meter cubed times a Pascal. So we can actually replace that joule, and I have it here, to, instead of joules, be meters cubed times Pascals. And now that makes more sense here, because you can see how Kelvins will cancel, moles will cancel, meters cubes cancel here, and Pascal cancels here. So whenever we are using this equation with R, if we know 3 out of the 4 properties, let's say we know pressure, volume, and Kelvin, we can put in the pressure into the equation, that cancels the Pascals, put in the volume into the equation, that cancels all the meters cubed, put in the temperature here, cancel the Kelvin, and all we're left with is the mole, which is the unit that we'll be looking for. We're going to look at some practice problem in a second. So the R is the gas constant, which is 8.31 meters cubed times Pascals over Kelvin times moles. And this is a number that you don't necessarily need to memorize. It is in your reference sheet in the exam. But in the reference sheet, it is labeled as joules per Kelvin mole. And so it does help to remember that those units, a joule, can be replaced with meters cubed times Pascals. And that usually makes it a lot easier to use the equation. So let's look at a practice problem, because this is just an equation. PV equals nRT. This is a very famous equation, probably one of the equations you'll remember the most after leaving this class. But at the end of the day, right now, to you, it's just an equation. So how do we use this? Let's look at a sample question. Now, you will need to remember the equation. So always remember, PV, pressure times volume, is equal to nRT, N being moles, R being the gas constant, T being the temperature. So let's look at a sample question from a past test. This is a paper 2 question. So let's look at this question. Calculate the amount in moles of pure nitrogen gas, which occupies 100 cubic centimeters at 101 kilopascals and 20 degrees Celsius. Use relevant information from the data booklet, show your working. Assume nitrogen behaves as an ideal gas. So this right here is telling us that we can use the ideal gas equation to solve this problem. This piece will not always be on the questions, but it's a pretty good indication of you having to use the ideal gas law on the ideal gas equation. If that is not on there, though, we still assume this is an ideal gas, because how to solve this for more real gases, non-ideal gases, is not part of your curriculum. So let's look at this in a separate place where we can work on it. Let's bring this over. So here we have the problem. Now, one of the first things I like to do with these problems is writing down what each piece of information is. So if we look at this, we have, I'm going to change colors here. Calculate the amount in moles. So we are looking for N here. We are looking for the amount in moles of nitrogen gas. And that's the very first piece of information we have, is that we are looking for the amount in moles. And then it tells us that it occupies 100 cubic centimeters. So that's the volume. So volume would be, let me actually put it on this side, on the bottom here. So volume would be 100 cubic centimeters. 101 kilopascals would be the pressure. We can tell by the units here that they're in pascals. So the pressure is 101 kilopascals and 20 degrees Celsius, which is our temperature. 20.0 degrees Celsius. Now we can tell from this that we have 3 out of the 4 properties, and then we're looking for the fourth one, number of moles. Now this should be pretty straightforward, because all we should have to do here is find or work using PV equals nRT, which is our ideal gas equation. Now, obviously, we need to rearrange this, because in this case, we are looking for N. If we're looking for N, we need to rearrange this equation so N is isolated, meaning we have to divide both sides by RT so that these cancel, and we end up with N is equal to PV over RT. Now, before we actually plug in these numbers, we need to make sure that each number is in the proper version or in the proper units. Because remember, volume needs to be in meters cubed, but here we have it in cubic centimeters. If we have 100 cubic centimeters, and we know, and normally you wouldn't have to show all of this work, but we know that 1,000 cubic centimeters is equal to 1 cubic decimeter. And remember, we need this in cubic meters. We know that 1,000 cubic decimeters is 1 cubic meter. Then that means that we need to divide this 100 cubic centimeters divided by 1,000 and then divided by 1,000 again. That gives us 0, and we'll put it here, 0.0001 cubic meters is over 100 cubic centimeters. Or we can just say 1 times 10 to the negative 4 cubic meters. Again, you don't actually need to show this math. You don't need to show the conversion. I'm just showing it here so you are aware of what we are doing. Again, pressure needs to be in pascals, not kilopascals. So we have 101 kilopascals, but we know that 1 kilopascal is equal to 1,000 pascals. Because that's what a kilo means. Meaning that 101 kilopascals is the same as saying 101,000. Put a 1 in there by accident. It's the same as saying 101,000 pascals. And again, we need to use pascals for the ideal gas equation. Finally, for temperature, we need to use Kelvin, not degrees Celsius. And this is the one that's most often going to be in the wrong unit, because most of the time we do give the unit of temperature in Celsius. So remember, to go from Celsius to Kelvin, all we have to do is add 273. So 20 degrees Celsius means, plus 273 means 293 Kelvin. Now that we have all of our units or all of our variables in proper units, now we can go ahead and plug them into this equation. So N is going to be equal to pressure, which we said is 101,000 pascals, times volume, which is 1 times 10 to the negative 4 meters cubed, divided by R, which remember R is that gas constant, and we do need to memorize it. It is 8.31 meters cubed times pascals over mole times Kelvin. And then finally temperature, which in this case is 293 Kelvin. So we can see here from looking at this that the units cancel. The pascals are going to cancel. The meters cubes are going to cancel. The Kelvin is going to cancel. And what we're left with is 1 over mole, or just moles. So here, I'm going to put this in a different color. N is going to be equal to 101,000 times 10 to the negative 4 divided by 8.31 times 293, which is going to give us 4.1815 times 10 to the negative 3 moles. And that's our answer. That's how many moles of nitrogen, I guess we'll put here N2, that's how many moles of nitrogen gas are in this container. Again, there's no chemical reaction here, right? There's nothing that is happening. What is going on here is that we are asked that we have a container that is at 100, has a volume of 100 cubic centimeters, at a pressure of 101 kilopascals, and a temperature of 20.0 degrees Celsius. And they tell us that that container is full of nitrogen gas, and asking us how many moles there are in that container. So they're giving us 3 out of the 4 properties in that container, and asking us for the 4th, which is moles of nitrogen gas. Now, this doesn't matter. It could be nitrogen gas, it could be carbon dioxide, it could be hydrogen, it could be oxygen. This is always going to be the same way in which we do things, because the ideal gas law works for any gas, because it's assuming that gas is behaving ideally. Obviously, that's not the case, and realistically speaking, it would be different, but that type of mathematics are out of the scope of the curriculum for AS chemistry. All right, let's go back. So we can see here that our 4.15 times 10 to the negative 3 answer was correct. So you get a point, because this is a 3-point question, you get a point for converting all of the variables into the proper units. So we get a point for converting the kilopascals for pressure into pascals, the volume from 100 cubic centimeters to cubic meters, and the temperature to Kelvin. We then get another point for using those values into the PV equals nRT equation. And then we finally get a point for the correct answer. So you can see how very simple equation that we're using, as long as we can remember the proper units we need to use in here, it becomes very straightforward and very easy to get all 3 points in this answer. That is the biggest thing though. You need to start remembering to write down the units like I did in our work. And let me bring the work back over. you need to start writing down the units of everything you use, because in ideal gas equations problems, and in this type of problem, these units become extremely important, because if you have something in the wrong unit, you end up with the wrong answer and you'll lose a lot of very easy points. So we need to start writing down the units for every variable, every measurement that we ever use, so we can make sure that we're using the correct units in our problems, and therefore get full points on these AS questions. Now, there is a variation of the ideal gas law, and we can use a simple algebra to essentially incorporate the mass and molar mass of a gas into the ideal gas law. And that's what this equation right here is. Molar mass is equal to mass times R times T over PV. This is a variation of the ideal gas law that uses the relationship between molar mass and the number of moles. Essentially, what we use here is a simple substitution in algebra. So if we have our equation, I'm going to use this in blue. So we have PV equals nRT. Let me lower the size here. PV equals nRT. Then we can actually use the molar mass equation. MR is equal to mass over moles. Remember, molar mass is equal to grams per mole. So molar mass is equal to mass divided by moles. Well, if we rearrange this equation, we get that moles is equal to mass over molar mass. Since we have moles here, and actually let me do this in a different color. I'm actually going to use this one in a different color. So PV equals RT. Since we have moles here is equal to M over MR, to mass over molar mass, we can substitute that N in PV equals nRT for M over MR. Meaning we get out of that, PV is equal to M over MR, mass over molar mass, times RT. We do this by substituting N for M over MR. If you can understand this, it actually makes all problems relating to ideal gas law so much easier. Because then we can get a bunch of different equations here from just this. We can rearrange this equation right here and get that PV is equal to MRT over MR. So if we were to solve for volume, we could use the molar mass and the mass to do that. We could also use it to solve for temperature, for pressure. But we could also then rearrange this to switch to the places of MR and PV to get the equation that we have up here, which is that MR is equal to MRT over PV. So you can memorize this, but realistically speaking, you will get a few questions wrong, or you won't be able to figure out a few questions if you simply memorize this equation. If you actually understand how this equation came about, how we're using substitution from the molar mass equation into the ideal gas equation to derive this, you'll be able to do this for a number of different things. You could do it for density, knowing that density is mass over volume. You could do it for the molar mass, like we said here, the mass, a number of different variables. All right. But you will be asked these kind of like higher level critical thinking questions. This is just an example of that application, the higher level critical thinking of the mathematics that are basically just algebra 1. But this is just one example. Like I said, we could do it with density as well. We could do it with a number of different things. So let's look at a question that uses this. A sample of ethanol vapor, C2H5OH, and they give you the molar mass of ethanol here, was maintained at a pressure of 100 kilopascals and a temperature of 366 Kelvin. Use the ideal gas equation to calculate the volume in cubic centimeters, and this is very important, that 1.36 grams of ethanol vapor would occupy under these conditions. The gas constant is 8.31 joules Kelvin mole. So they even give you the gas constant here. Let's I can put this in a way that we can use it. Let's try this. So if we look at this equation, or this problem, we can, again, start by looking at what they're giving us. So they're giving us that we have ethanol with a molar mass of 46.0. So we can write here MR, in this case, is 46.0 grams per mole. Was maintained at a pressure of 100 kilopascals, so they give us the pressure as well, which is 100 kilopascals. And a temperature 366 Kelvin. So this is pressure, this is temperature, this is MR. So the temperature is 366 Kelvin. So we don't even need to convert that, it's already in Kelvin, that's wonderful. And then it says, use the ideal gas equation to calculate the volume. So we're looking for V for volume, but we have to be very careful because we're looking for V, but we're not looking for V in meters cubed. We're looking for V in cubic centimeters. So we gotta be careful and conscientious that when we're looking for that answer, when we calculate the answer, it will be in cubic meters and then have to be converted. The very last piece of information they give us is that we have our mass, because it's in grams, is 1.36 grams. Now, if we look at this, if we think of the ideal gas equation, the ideal gas equation is PV is equal to nRT. Now, here is where we gotta make a decision in our approach, because we have pressure, we have volume, or we're looking for volume at least. We have temperature, but we do not have number of moles. We have instead the molar mass and the mass of this compound. Now we have two options here. We can either reform this equation using the equation for molar mass, and then recreate a new equation that we can use. Or we can use the molar mass and the number of mass, the amount, in order to calculate N and then plug it into this equation. I'm going to do the first one. The reason to do the first one, and the reason why the first one makes more sense, is because it allows us to do everything in one step, which minimizes the amount of error we introduce into our problem. Again, molar mass is grams per mole, meaning it's mass divided by moles. Meaning the number of moles is equal to mass divided by molar mass. If we replace or substitute this N into our, actually I'm gonna circle the other one. So if we look at this N is equal to mass over molar mass. That means we can replace the N in the ideal gas equation for it, giving us PV is equal to mRT over mR. Since we're looking for volume, we want to isolate the volume, all we need to do is divide both sides by P. So these P's cancel out, and we get that the volume is equal to mRT over mRP. And this is why I told you not to just memorize the other equation. Because here, you'll notice how in the other equation, we had it in a form where MR was equal to other stuff, to MRT over PV. But in this form, we're isolating volume because that's what we are calculating for. That's what our unknown is. Now that we have the equation and we have all the data, we can plug it in. Obviously, we still need to make sure that all our data has the proper units, which it doesn't because our pressure is in kilopascals. So 100 kilopascals is the same as saying 100,000 pascals, because 1 kilopascal is 1,000 pascals. Our temperature is in Kelvin, so that's good. Grams for mass, that's fine. Molar mass is grams per mole. So now we can actually use this equation in order to solve our equation, our problem here. So we're going to use this equation. Volume is equal to mRT over mRP. That means that volume is equal to mass, which is 1.36 grams, times R, which as we said is 8.31. And again, they give it to you in joules per Kelvin mole. I prefer to write this as m cubed times pascals over Kelvin mole, because then the units make more sense when you cancel them. times temperature, which is 366 Kelvin, over, make sure, oh no, let me see if I can backtrack a little, over MR, which is the molar mass, which was 46 grams, 46.0 grams per mole, times pressure, which we said was 100,000 pascals. And you can see here how these units start canceling each other out. We can see how the grams from the mass and the molar mass cancel out. The moles from the molar mass and the constant cancel out. The kelvins from the temperature and the constant cancel out. And then the pascals from the constant and the pressure cancel out. So that leaves us with our volume being equal to 1.36 times 8.31 times 366 divided by 46 times 100,000. And what we get from that is 8.99 times 10 to the negative 4. And then again, you got to remember that this is, if we look at what unit we had left, in meters cubed. But we are being asked for the volume in centimeters cubed. So we need to convert this. Again, if we combine this, the conversion, all we need to do in order to turn this from meters cubed to centimeters cubed is realize that 1 meter cubed is equal to 1,000 cubic decimeters. And then 1 cubic decimeter is equal to 1,000 cubic centimeters. So we're going to do 8.99 times 10 to the negative 4 times 1,000 times 1,000 again. And that gives us 899 cubic centimeters. Or a bit under a liter, or 900 cubic centimeters or so. So 899 cubic centimeters, and that is our answer because they wanted the answer in cubic centimeters. Again, just to show you how important following up on all of these units is when we're doing ideal gas calculations. Because without those units, we would not be able to understand that this answer here is in meters cubed, and so needs to be converted to centimeters cubed to give you the right and correct answer. So we can look now at the mark scheme, see that 899 cubic centimeters is the correct answer, and this is a 4-point question. You get 1 point for figuring out the number of moles of ethanol that you had. And again, we did that by incorporating our equation for molar mass into the equation for the ideal gas law. You could have done it separately like they do here in the mark scheme, where they just divide the mass by the molar mass to get the number of moles. You will still get this point in the way that we did it, because you are showing that you understand that knowledge by combining the equations. Then you get a point for using the ideal gas equation correctly and having it correctly set up. And then you get 1 point for getting the answer in meters cubed, and then 1 point for getting the answer correct in the conversion to cubic centimeters. So you're able to get full points if you do the way that we did, or you could do it separate like they did here, where you find n first and then plug n into the other equation. Either way is fine. It's whatever makes more sense to you. All right. So let's go to the next slide. Oh, sorry. So I was in the same slide. So there are a number of concessions that they will make on Cambridge exam paper 2 when it comes to this mathematics, and you can see them all here. For example, the first concession, which is on that first piece that we saw, is that if you flip the equation, so if instead of putting B is equal to nRT over P, you actually put B is equal to P over nRT, you will lose the third and the fourth mark, but you will still get the first 2 points if you did them correct, if you did the first part correctly, and then if you flip the second one. The reason you will still get this point is because you're using the correct equation, you're just doing the algebra wrong. So you wouldn't get the point for the answer. Now you can see that if a final answer is 0.899, which is in cubic decimeters, then it says award 2 plus M1. So award mark 2 plus mark 1. So you get 2 points out of that. And same thing here, if it's 912, which I'm not sure where the 912 comes from, but if you get a 912 as your answer, which is outside of the range of the accepted answers that they have, then you get mark 3, mark 3 plus mark 1. So then you have a bunch of other notes here. If 1.36 or 46 or 46 over 1.36 used as a number of moles, and the mark 2 and mark 4 are not available. So if you messed up with the moles, you wouldn't be able to get mark 2 or mark 4, but you still be able to get mark 1 and mark 3. If pressure is 100, if you forget to convert the pressure to 100,000, then unless the answer is 0.899 cubic decimeters, you need to deduct mark 3 and mark consequentially, meaning that you wouldn't get mark 3 if you used 100, and then you kind of follow that mistake to the answers. So they make, of course, if you didn't understand these things, that's fine. But what I'm saying is, even though it's 4 points, and if you make a mistake here at the beginning, it kind of cascades down, they have a lot of concessions where, like, if you make one small mistake, like using 100 for the pressure to 100,000, you will still be able to get other points. You will obviously not get full points. You will still lose a mark in this case, which will be mark 3, but you still will be able to get mark 1, 4, and mark 1, 2, and 4. All right. So they do have concessions. They do have essentially what we usually call partial credit for these type of problems. So just be aware of that. It makes it easier. It kind of takes the pressure off of you when it comes to this math. Finally, this I believe is the last topic. We'll do this and we'll do a problem that goes along with it. But we can, for ideal gases, use ratios when it comes to the volumes and the moles. In chapter 3, we learned about Avogadro's hypothesis, saying that at room temperature and pressure, all gases occupy a volume of 24 cubic decimeters. Well, that's actually tied to the ideal gas laws. If we look at PV equals nRT, if we have room temperature and pressure, meaning pressure and temperature are constants, then what Avogadro's law is saying is that 1 mole, which at that point will be a constant, is always going to have a volume of 24.0 cubic decimeters. All this is that volume comes from, if we rearrange this equation, B is equal to nRT over P. If we put 101,000 pascals, which is what room pressure is, and 298 Kelvin, which is what room temperature is, and 1 mole for N, and R is a constant, it's 8.31. What we get from putting all those numbers into the equation is 24.0. That's where Avogadro, or 24.0 cubic decimeters, essentially 0.024 cubic meters. That's where Avogadro's law comes from, Avogadro's hypothesis comes from. A gas, because of the ideal gas laws, will occupy 25 cubic decimeters, or 1 mole of a gas will occupy 25 cubic decimeters under room temperature and pressure, because that makes the pressure, the temperature, and the moles constant in this equation. Now, that means that we can use the mole ratio and supplement them for volume ratios whenever we're doing math with ideal gases. So in short, what does this mean? Because that's a lot of very complicated theory behind a very simple process. If we have, for example, the equation for the creation of ammonia, which is what we call the Haber process, N2 gas plus 3H2 gas makes 2NH3 gas. We know from chapter 3 that that means we have a 1 to 3 to 2 mole ratio. 1 mole of nitrogen is equal to 3 moles of hydrogen, which is equal to 2 moles of ammonia. Well, that mole ratio can actually also be used only for ideal gases with volumes. For ideal gases, and I'm going to put here again, for ideal gases. For ideal gases, that will mean that that 1 to 3 to 2 ratio can be applied to the volume of the gas as well. Meaning if we had 10 moles of cubic centimeter or 10 cubic centimeters of nitrogen reacting, because the ratio of nitrogen to hydrogen is a 1 to 3 ratio, 10 cubic centimeters of nitrogen would need 30 cubic centimeters of hydrogen. The same way 1 mole of nitrogen needs 3 moles of hydrogen, 10 cubic centimeters of nitrogen needs 30 cubic centimeters of hydrogen. Or essentially 1 cubic centimeter to 3 cubic centimeters. Why? Because since in the ideal gas law, we're looking at constant temperature, constant pressure, then the moles and the volume of the gas have a ratio or relationship between them. And then these two, if you had 10 cubic centimeters of N2 reacting with 30 cubic centimeters of H2, it will make 20 cubic centimeters of NH2. Why? Because the ratio between the moles, that 1 to 3 to 2 ratio, is equivalent not just for moles, but also for volume for an ideal gas. So 1 to 3 to 2 is the same as 1 cubic centimeter to 3 cubic centimeters to 2 cubic centimeters. And then we just multiply all that times 10 cubic centimeters to 30 cubic centimeters to 20 cubic centimeters. So we can use mole ratios directly with volumes with ideal gases. Again, this is not for every equation. We wouldn't be able to do this with aqueous solutions or solids. We can only do this with ideal gases. And this comes in very, very handy in certain equations or certain problems in the AICE exam. Some problems that will be very complicated in the AICE exam can be made much, much simpler by this idea of doing ratios of the volumes of the gases instead of their moles. Because it essentially eliminates any need to convert from volume to moles and then back all the way around. So let's look at this problem. 10 cubic centimeters of ethane is burned in 45 cubic centimeters of oxygen at a pressure of 101 kilopascals and a temperature of 200 degrees Celsius. Complete combustion takes place. What is the total volume of gas present and the reaction is completed? Measure under the same conditions. So we can, I'll bring this over so we can work on it a little easier. If we look at this problem, first of all, we need an equation because they're talking about the combustion here, a combustion reaction. Now, with the combustion reaction, we have ethane is burned in oxygen. And again, you wouldn't know what ethane is right now, but you will later in the year. Ethane is C2H6, and that's a gas, is burned in oxygen, O2 gas, to create in a complete combustion. If this is a combustion reaction, we learn in honors chemistry, because we have carbon and hydrogen, that the products will be CO2 gas and water, H2O, which will also be a gas because of the heat created by a combustion. We will obviously need to do balancing here. So we have 2 carbons, so we put 2 carbons here. We have 6 hydrogens, so we have H2 here, so 3 times 2 is 6. And that's where we get into a problem. We have 2 times 2 is 4, plus 3 is 7 oxygens. But because we have a 2 here, we will have to put 3.5 as our coefficient. 3.5 times 2 is 7. We can't do that, right? We can't have a decimal as a coefficient. But what we can do is, because that's 0.5, we can multiply all of these coefficients times 2. So we get 2C2H6 times 7O2 times 2 times 2 is 4CO2 times 3 times 2 is 6H2O. And that gives us a 2 to 7 to 4 to 6 ratio. Now, if we look at that, we get 2 times 2 is 4 carbons. There are 4 carbons here. 2 times 6 is 12 hydrogens. 6 times 2 is 12 hydrogens. And then 7 times 2 is 14 oxygens. We have 8 oxygens here. 4 times 2 plus 6 is 14. So it makes the balancing a lot easier. Now that we have that, we can look at the numbers they gave us in the problem. So the problem says we have 10 cubic centimeters of ethane. So we have 10 cubic centimeters of this. And this is my preferred way of doing these type of problems, where we just write what they gave us underneath each one of the products and reactants. So we have 10 cubic centimeters of ethane reacts with 45 cubic centimeters, or is burned with 45 cubic centimeters of oxygen. And it tells the pressure is 101 kilopascals and the temperature is 200 degrees Celsius. We could, and the way that most of y'all would go around doing this, is to start using these numbers, 101 kilopascals and 200 degrees Celsius, to convert these volumes to moles. Because we have pressure, we have temperature, and here we have volumes. So we could, in theory, use PV equals nRT to convert to moles. But that would take a really long time. This is a multiple choice question in paper 1 that shouldn't take you more than 1.5 to 2 minutes to do. So how do we do this quickly? Well, we can, again, because we have volumes here, we can use the mole ratios as the ratios, not for moles, but for the volume. Now, this is still a stoichiometry question, so we still need to undergo a few little pieces of critical thinking. First of all, it says 10 cubic centimeters of ethane is burned in 45 cubic centimeters of oxygen, not reacts with, meaning that this could be a problem where we have an excess reactant. And we need to keep that in mind. Number 2. What is the question asking for? The question says, what is the total volume of gas present? Not the volume of CO2, not the volume of water, not the volume of the products, the volume of gas. When the reaction is complete, measure under the same conditions. Meaning that if we do have an excess reactant, we need to consider that that excess reactant is also a gas, and we'll have leftover volume that we need to consider. So let's look at this excess reactant or limiting reactant problem here. Essentially, we can use these ratios to tell whether we have an excess reactant or not, because, and I'm going to use right here, if we have 10 cubic centimeters of ethane, according to this 2 to 7 ratio, then in order to figure out how much oxygen that will react with, I have to do 10 times 7 over 2. Why 7 over 2? If we put this in a much bigger way, if we have 10 cubic centimeters of C2H6, because these are equivalent to moles, we can do the same as a mole ratio. We have 2 cubic centimeters of C2H6 is equivalent to 7 cubic centimeters of oxygen, according to our ratio here in the reaction. Well, 10 divided by 2 is 5, times 7 is 35 cubic centimeters of oxygen. Meaning, even though we have, this is how much we have up here in blue, even though we have 45 cubic centimeters of oxygen, we don't need 45 cubic centimeters of oxygen to react with 10 cubic centimeters of ethane. If we use up all 10 cubic centimeters of ethane, according to the mole ratios 2 to 7, we only need 10 times 7 over 2, or 35 cubic centimeters of oxygen. Now, if we only use 35 cubic centimeters of oxygen, then that means that left, or created, or whatever you want to call it, we are going to use all of our ethane, so we have 0 cubic centimeters left. But since we have 45 cubic centimeters of oxygen and we use 35, we still have 10 cubic centimeters of oxygen left. We need to incorporate that into our answer because look, it's a total volume of gas present. Oxygen is a gas and we have 10 cubic centimeters of it present left. Now, that's not the answer though. Why? When that 10 cubic centimeters of ethane reacts with the 35 cubic centimeters of oxygen, it creates two things. Initially, we had 0 cubic centimeters of carbon dioxide and 0 cubic centimeters of water. But when these two reacted together, when 10 cubic centimeters of ethane reacted with 35 cubic centimeters of oxygen, it made carbon dioxide and water. If we look at ethane to carbon dioxide, we had a 2:4 ratio between ethane, C2H6, and CO2. Well, a 2:4 ratio is the same as saying a 1:2 ratio. Meaning that we're going to create twice as much carbon dioxide as the ethane that we use. So 10 cubic centimeters of ethane means that we create 20 cubic centimeters of carbon dioxide. Again, for those of you who need to actually see the mathematics, and again, it's something that you should really start working on being able to use in your head, but if we have 10 cubic centimeters of ethane, C2H6, 2 moles or 2 cubic centimeters of ethane is equal to 4 cubic centimeters of carbon dioxide. So 10 divided by 2 is 5, times 4 is 20 cubic centimeters. So we're creating 20 cubic centimeters of carbon dioxide. There was no carbon dioxide originally. That means that at the end we have 20 cubic centimeters of carbon dioxide left. Now, we're almost there because that's not the only gas being created, right? Water is also being created. Now, for water, we have a different ratio. 2 cubic centimeters of ethane, C6H12, or not H12, oops, H6, C2H6. If we look at here, we have 2 to 6 ratio. A 2 to 6 ratio between ethane and water. So 2 cubic centimeters of ethane is equal to 6 cubic centimeters of water. Or again, a 2 to 6 is the same as saying divided by 2 is a 1 to 3 ratio. So if it's for every 1 cubic centimeter of ethane, we make 3 cubic centimeters of water. So for every 10 cubic centimeters of ethane, we make 30 cubic centimeters of water. Again, if we need to see the math for that, 10 cubic centimeters of ethane, C2H6, 2 cubic centimeters of ethane from the ratio, from the mole ratio, but we can use it here. Again, the whole point of this, we can use the mole ratio as a volume ratio because we're dealing with ideal gases. 2 cubic centimeters of ethane are equal to 6 cubic centimeters of water. Which means 10 divided by 2 is 5, times 6 is 30 cubic centimeters of H2O being created. So we use /create, let me just put here. We create 30 cubic centimeters of ethane, of water, sorry, which means that we have, at the end of this, let me put this in purple, we have the 30 cubic centimeters of water that are created. So again, the question is, what is the total volume of gas present? Well, at the end, left over, we have 0 mole or 0 volume of ethane plus 10 of oxygen that we have left because we only use 35 out of the 45 plus 20 cubic centimeters of carbon dioxide we created plus 30 cubic centimeters of water we created. So it's 30 plus 20 plus 10 is 60 cubic decimeters of gas in total. Meaning that the final answer here should be D. Had you converted every single one of these volumes to moles using P equals nRT, and then added all of those moles up, and then I converted back to cubic centimeters, and having to do the conversions from cubic meters to cubic centimeters, it would have taken a much longer time to get this answer. Obviously, this took me more than 2 minutes because I'm explaining every single step. But this should be something that you should be able to easily do in your head in moles. It is a high-level critical thinking question, but once you have the equation with the ratios, all you have to do is start doing the ratios between each compound. And then you should be able to get that answer of 60 cubic centimeters. So if we look here, we see that the answer is C. If you need to, watch this video a few times, watch this section of the video a few times until you understand this. Because if you're able to understand this, it doesn't just make this type of problem easier. It allows you to look at math in a different way that expands your way of doing things in Cambridge, especially for mathematical work and stoichiometry work. And it makes it a lot faster and a lot easier than having to work out every single step. All right. Move over. Well, I think that is it for this section. We are going to look at the liquid state in the next video. But for gases, this is all you need to do, and it does require a lot of mathematics. So my recommendation is go out there, practice, 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 look for past paper questions, and try to do these problems with the ideal gas equation and these ratio problems with the volume. I'll see you all in the next video.